Good morning, students. Welcome to the another first video of online classes. Till now, we have completed two chapters. I hope you all practice these two chapters. Now we are in the third chapter. Uh, the third the third chapter is about machines. Okay. So today we will start the chapter third, which is machine. Okay. So now the content in that chapter three is the first one is machines. We'll read the definition. Now we'll learn about some technical terms related to the machines, load, effort, mechanical advantage, which is referred as abbreviated as M dot A, and velocity ratio VR, work input, work output, efficiency eta. Okay, this symbol is read as eta. Okay, so now principle. Then we'll discuss about the principle of machines. Okay, then next relation between eta, ma and vr, then levers, principle of levers, which is otherwise known as mechanical advantage of a lever. Okay, then we'll read about uh, kinds of levers. Okay, class 1 lever, class 2 lever and class 3 levers. Then some examples of levers which is found in human body. Okay, let us begin with the first one, machines. Okay, a machine is a device to overcome a large resistive force. Resistive force means what? Load, we can say, by applying a small force. The small force is effort. Okay, or to gain speed, to change the direction and the point of application of force. Okay, so a machine is a device. Simple, in simple words we can say that the machine can uh, help us in daily life to reduce our hard works. Okay, so then a machine does not work itself. When energy is supplied to it or work is done on it, a machine does same useful work. Okay, so a machine cannot be work without help of any other energy. Okay, so energy has to be supplied. Either we have to give the physical energy or we have to give the some form of energy like fuel, etc. Okay, to work a machine. Then some functions of machine. Okay, the first one is it is used to multiply force, used as a force multiplier. This means uh, see, by applying a less force we can get the biggest force, the force we have applied before. Okay, so this is called as a force multiplier. Then it makes a force applied at one point available at some other desired point. Okay, by the machines we can apply a force at some point, but that force can be available in other any other point. Okay, then third one is it changes with direction of force applied. Okay, and it increases the speed. Okay, so these are the some functions of simple machines. Okay, now some technical terms related to machine. Okay, the first one is load. The resistive force to be overcome by a machine is called load, and it is always given by the capital L. The point where the energy is obtained by overcome to a load is called the load point. Okay, got? So where the output has to be get, that point is known as load. Okay, effort. Effort is what? The force applied on a machine to overcome the resistive force. Resistive force means load, is called effort. Okay, okay, the effort force is always we can say that the supplied energy. Okay, and the point at which the energy is supplied to the machine by the resistive force is called the effort point. Okay, now you got you understood what is load point and what is effort point. then mechanical advantage. Okay, the mechanical advantage, it is abbreviated as MA. So it is the ratio of the load to the effort. Okay, it is the ratio of the load to the effort. So mechanical advantage can be given by load divided by effort. Okay, we can write MA is equal to L by E. Okay, since it is the ratio of two similar quantities, that's why the mechanical advantage has no units. Okay, got. The next, the term is velocity ratio. Okay, it is abbreviated as VR. Okay, so this is also a ratio. uh, it is the ratio of the distance traveled by the effort to the distance traveled by the load in the same interval of time. Okay, at a particular interval of time, at a particular same interval of time, how much the effort traveled, and at that time how much distance the load traveled. We have to take the ratio, then we'll got the velocity ratio. Okay, so it can also be defined as the ratio of velocity of effort to the velocity of load. Okay, so it can be written as like this: the velocity ratio is equal to distance traveled by effort divided by distance traveled by load. Now, or velocity is equal to velocity of effort by velocity of load. Then, since it is a ratio of similar quantity, so like mechanical advantages, it is also a ratio of similar quantity. That's why uh, velocity ratio also do not have any unit. Okay, then then work input. Okay, the energy supplied or work done on the machine by the effort is called input or work input. Okay, the energy supplied to running a machine, that is known as input work. Okay, then work output, energy obtained or work done by the machine on the load is called output or work output. Okay, the machine's output is known as work output. Okay, the work is obtained by the machine is known as work output. Then efficiency eta, so it is the ratio of useful work done by a machine, which is known as work output, to the total work done on the machine, which is work input. Okay, so we can say that efficiency eta is equal to work output divided by work input. It is usually expressed as a percentage. Okay, as it is also a ratio of same quantities, that's why it do not have any unit. So we can write efficiency eta is equal to work output divided by work input. So as we are calculating in a percentage, we'll multiply by 100, we'll get the efficiency percentage of any machine. Okay, so for ideal machines, the work output is equal to work input. That's why the efficiency of the of the ideal machine is always 100%, but practically it is not possible. Okay, so ideal machine is only for theoretical purpose. Okay, then however in practical, no machine is 100% efficiency due to some reasons, such that we can say that the main thing is resistive power of the machine, like friction. Okay, now let us read one by one point. Smoothness in moving parts, the moving parts of a machine are not properly smooth, that's why it reduces the working capacity or a working efficiency of the machine. Then elastic of a string. Okay, if there is a elastic, so you know that the string is not perfectly elastic, then if the string is not properly elastic, then it will also consume some energy. That's why the work output should be less than the work input. Then next one is rigidness of part. Okay, if any part is not perfectly rigid, then this also gains some energy to performance. That's why the output energy or the output work done will be less. Okay, weight of moving parts also uh, have a importance in the efficiency of the machine. That's why if the weight of the part is not weightless, if the part of the machine is very heavy, then it also consumes some energy. That's why the efficiency of the machine will be affected. Okay, then principle of a machine. Okay, when energy is supplied to a machine by applying the effort, it does some useful work. Okay, then we can say that the point at which the energy is supplied to a machine by applying the effort is called effort point, and the point where energy is obtained by overcoming the load is known as load point. These two points already we have discussed. Okay, at the point which is where we are applying the force, which is no if we are applying the effort, is known as the effort point, and where we are getting the output, that point is known as a load point. Okay, so input energy is equal to, we know that work done at effort point. So work done at effort point, how to calculate? Effort multiplied by distance of the point of application of the effort. So similarly, we can calculate output energy is equal to work done at load point, and which is equal to load multiplied by displacement of point of application of the load. Okay, so now what we will do, for a perfect or ideal gas, so sorry, a ideal machine, output energy is always input energy. Okay, but in practical machines, work output is always less than work input, because of the we have read those points about why the in practical we cannot get a 100% efficiency machine. Okay, so as some of the energy is wasted in overcoming the friction between different moving part in the machine, that's why always work output is less than what work input. Okay, now let us establish a relation between eta, ma and vr. Eta stands for efficiency, ma stands for mechanical advantage, and vr stands for uh, velocity ratio. Okay, now we know that uh, work input is equal to effort multiplied by the displacement of effort. Here effort is denoted by E and the displacement of effort is given by dE. Okay. Similarly, work output is equal to load multiplied by displacement of load. Okay. So here load is given by L and displacement of load is given by dL. Okay. Now we know that the efficiency eta is equal to work output divided by work input. Now we can divide like this: L dl but divided by EDE, and we can separately write like this: L by E multiplied by dl by dE. But taking this dl to the denominator, it will be 1 by dE by dl. Okay, but we know that L by E, which is mechanical advantage. So mechanical advantage is equal to load by effort, and we know that dE by dl, which is equal to what? Velocity ratio. So we can replace these values with here we can replace the values like this. Then we will get efficiency eta is equal to ma by vr. So efficiency eta is equal to the ratio of mechanical advantage to the velocity ratio. Okay, so we can calculate ma from this equation like this: mechanical advantage is equal to velocity ratio multiplied by eta. Okay, so thus the mechanical advantage of a machine is equal to the product of its efficiency and velocity ratio. From this we can write this definition. Okay, so this is all about the relation between eta, mechanical advantage, and velocity ratio. The next, levers. Okay, A lever is a rigid, straight or bent bar which is capable of turning about a fixed axis. Okay, now here the axis is what? The fulcrum. Okay, and the input force is known as effort, and the output force, which is known as resistance, or you can say that as a load. Okay, so for levers, so this is the axis, and it is always turning about this axis only, which is known as fulcrum. Okay, now you just remember that uh, the input force, which is effort, is always in the opposite direction of the output force, which is load. Okay, now discuss principle of a lever. Also it is known as a mechanical advantage of a lever. So now see, there are three type of levers already, you know, in the uh, lower classes. Okay, so the distance from fulcrum to effort is known as effort arm, and the distance from fulcrum to load is known as load arm. So in class 2 lever also like that, in class 3 lever also like that. Okay, now you can say that the suppose you can see any of the figure, the moment of the load about the fulcrum is equal to the moment of load about the effort about the fulcrum. Here see this one, the L is downward, here also effort is downward. So here the load arms, the load arm is in clockwise direction, but the effort arm is in acts in anti-clockwise direction. So you can say that the anti-clockwise moment is equal to the clockwise moment. Anti-clockwise moment of load effort is equal to the clockwise moment of load. Okay, so now we can write like this: load, the moment of load can be written as load into load arm, and the moment of effort arm can be written as effort into effort arm. So force, and this one is the distance from the axis. Okay, now uh, from the figure we can write L load is equal to L, and load arm is how much? Fe is the load arm, Bf is the load arm, and effort arm is equal to AF. Okay, in all the cases effort arm is equal to AF. Okay, now we have to calculate by cross multiplication. We'll get take E to this side and take BF this side. We'll get L by E is equal to A by AF by BF. Okay, now L by E is equal to AF by BF gives you MA. So we know that effort arm by load arm gives you the mechanical advantage. Okay, then we can write MA is equal to effort arm AF divided by load arm BF. So here we can replace L by E with MA, we'll get the mechanical advantage effort arm AF divided by load arm VF. Okay, so this is all about the principle of lever, and it is also known as the law of levers. Okay, now we can say that the mechanical advantage of a lever is equal to the ratio of length of its effort arm to the length of its load arm. So okay, now depending upon this we can say that if effort arm is equal to load arm, then mechanical advantage should be equal to 0. Then if effort arm is less than load arm, then always mechanical advantage is always less than 1. Okay, and similarly if effort arm is greater than load arm, then mechanical advantage is always greater than 1. Okay, now kinds of lever. Okay, I'll just put this picture. You all know about the kinds of levers. There are three type of levers, and this is your work. I am left this much part upon you, that what are the kind of levers and what are the examples. You just follow the book and make a note of that. Okay, so I'm just telling that uh, definitions. Okay, in class 1 lever, fulcrum is in between A effort and load. But in class 2 liver, load is in between effort and fulcrum. Okay, then in class 3 liver, effort is in between fulcrum and load. Okay, so these three are the just definitions. You can get more examples in your book. You just follow your book and make a note of that. Okay, how many kinds of livers are there, what are the examples. Okay, now I'll discuss about livers in human body. Okay, let us look at the picture. Okay, here there is a human skull, and here uh, the leg part, and here the arm. Okay, so one by one we'll discuss. Okay, now see the first one. Okay, this one here, the action of nodding of head, it is work as a liver, class 1 liver. So how? See, the action of nodding of head, in this action the spine acts as a fulcrum and load is at its front part, while the effort E is at the rear part. Thus, this acts as a class 1 lever. You can clearly see the figure like this. Okay, the load, which is written as R here, resistance. Okay, so load is on the front part and effort is on the back part or the rear part of the fulcrum, where fulcrum is what? Spinal cord. Okay, spine. Okay, that's why it is act as a class 1 lever. Okay, another example also given, seizures. Okay, now look at this picture. Okay, raising the weight of the body on the toes. Okay, so this acts as a class 2 lever. How? See, the toe is act as fulcrum, and the body weight is act as load, which is act downward, but the effort we are giving upward. That's why here the load will be in between effort and fulcrum. That's why it is class 2 lever. Now look at this picture at the arm. Okay, raising a load by forearm. Sorry, if you are raising a load on the forearm, then the load will be here. So load will be act downward, and this here it will act as a fulcrum, and effort will be on our arms. Okay, so we can say that the elbow joint act as a fulcrum here, and the biceps acts as a effort. Okay, now we are putting the load at our palm, on the palm. That's why here the effort will be in between fulcrum and load. That's why it is class 3 lever. Okay, okay, I hope you understood this much. Okay, if you have any doubts about this chapter, then let me know in the group. So thank you for watching. Okay, we practice all the exercises. Also you see the examples. If you have any doubts, just ask the example and try to solve exercise 3a question answer. Okay, if you have any doubt about that question answer, you can ask me. Okay, so thank you for now, and in the next video we'll learn about the pulley. Okay, thank you.